Continuing on Physical Chemistry Chapter 3, we're beginning Section 4 now. Now we're going to talk about how do you calculate changes in entropy. So remember, ds, the differential of entropy, is equal to dq reversible over temperature. So delta S is going to be the integral from state 1 to state 2 of dq reversible over temperature. And remember, delta S reversible is equal to delta S irreversible since it's since it's a state function. And remember, we're always talking about the system, not the surroundings. That's implied because we're always talking about the system. So let's start with the obvious, a cyclic process. For any state function, the cyclic process, the change in the state function is equal to 0. Entropy is a state function, therefore the change in entropy for a cyclic process is equal to 0. Now let's talk about a reversible adiabatic process. Well, if it's adiabatic, dq reversible is equal to 0. Therefore, the change in entropy is going to be equal to 0. Now let's talk about a reversible phase change at constant temperature and constant pressure. Well, we have delta S is equal to the integral from state 1 to state 2 of dq reversible over t. Temperature is constant, so we'll pull that out. So we get 1 over t times the integral from dq reversible. The integral of dq reversible is just q reversible over t. We said constant pressure, therefore it's going to be qp over t, or delta H over t. Well, that's weird. Oh, I see. Okay, so the t was there the whole time. Got it. So the change in enthalpy, remember, that's the latent heat of transition. So this is the heat it's going to take to do the transition, such as melting or whatever. If delta H is greater than 0, then delta S is going to be greater than 0. If delta H is less than 0, then delta S is less than 0. Now what about a reversible isothermal process? Pressure is not necessarily constant. Isothermal means constant temperature. Delta S is going to be 1 over t times the integral of dq reversible over t, so we just get q reversible over t. Entropy is not very pressure sensitive though anyway. Now what if we have a reversible change of state in a perfect gas? Like we're going from volume 1 temperature 1 to volume 2 temperature 2. Then dq reversible is equal to dq, or du, internal energy, minus the differential of work. That's by the first law of thermodynamics. So the differential of entropy is going to be dq reversible over t, just like we had before. dq reversible is going to be cv dt plus pdv. Remember, this is from the work, this is from the change in the internal energy. This is only true for a perfect gas, though. So we get dq reversible, that's going to be C, the heat capacity constant volume, times the differential of temperature, plus the number of moles times the gas constant times temperature divided by volume times the differential of volume. Then we're going to divide that by t. So we get dq reversible over t is equal to cv dt over t plus nr dv over v. Now that we have separation of variables, we can take the integral. Now, the integral of dq reversible over t, that's our delta S, change in entropy. And the integral from state 1 to 2, that's the heat capacity constant volume times the differential of temperature divided by temperature, plus nr, these are constants, times the integral from state 1 to state 2 of dv over v. So we get delta S is equal to the integral from state 1 to 2 of cv, heat capacity constant volume, which is temperature dependent, divided by temperature times the differential of t, plus nr times the natural log of v2 over v1. So if v2 over v1, then nr ln of v2 over v1 is going to be positive. If t2 is greater than t1, then the integral from state 1 to state 2 of cv of t dt over t is going to be positive. So we're going to assume that cv is constant over the temperature range. Then we get delta S is roughly equal to the heat capacity constant volume times the natural log of temperature 2 over temperature 1 plus the number of moles times the gas constant R times the natural log of V2 over V1. So these two ratios should tell you two things. One, if your system is expanding, your entropy is going to increase, or if your system is being heated, your entropy is going to increase. The 6, irreversible change of state in a perfect gas. S is a state function. Therefore, the change in entropy for a reversible process has got to be the change in entropy for an irreversible process. Now that doesn't mean, though, that the Q of reversible process is equal to the Q of an irreversible process. For one thing, temperature plays a role. Okay, now what about constant pressure heating, assuming no phase change? Then we get dq reversible is equal to dq at constant pressure, and that's equal to the heat capacity at constant pressure times the differential of temperature, and that's equal to temperature times the differential of entropy. And then the differential of entropy is equal to differential of Q reversible over T, and that's equal to the heat capacity at constant pressure over T times dt. So that gives us delta S is equal to the integral from T1 to T2 of heat capacity constant pressure divided by temperature with respect to temperature. And this is assuming constant pressure, no phase change. Now, if the heat capacity at constant pressure is constant, then delta S is equal to the heat capacity at constant pressure times the natural log of T2 over T1. And that's true whether it's reversible or irreversible. Now let's say we have just any general change of state. P1 T1 to P2 T2. We can't do that yet. We have to wait until we get to chapter 4, section 6. For problem number 31 in this chapter, just assume it's an ideal gas and gives PV equals nRT. Now let's talk about an irreversible phase change. Now, let's say we have some liquid water. It's at negative 10 degrees Celsius in 1 atmosphere. This is unstable. This is not, this however you manage to do it, it's not going to stay that way. So this is going to irreversibly turn into ice at negative 10 degrees Celsius in 1 atmosphere. Now, how can we find the calculations to do this? Well, what we do is we find the reversible paths to do this. We can take this liquid water, minus 10 degrees at 1 atmosphere, and we can convert it to liquid water at 0 degrees Celsius in 1 atmosphere, and then we can reversibly convert it to ice at 0 degrees Celsius in 1 atmosphere, and then we can reversibly convert it to ice at negative 10 degrees Celsius in 1 atmosphere. We can get a reversible entropy change for this part, a reversible entropy change for this part, and a reversible entropy change for this part. This is prime and double prime, just to keep it. Now we can do this partly because entropy is extensive. So since entropy is extensive, the change in entropy is going to be just the entropy of this reversible step 1, entropy of reversible step prime, and reversible step double prime. Now, the change in entropy reversible here, this is just the heat capacity for liquid water times the natural log of T2 over T1. For this part here, the change in entropy is going to be the latent heat of freezing divided by temperature, and that's going to be equal to the negative the enthalpy of melting divided by temperature. Freezing, melting are opposites. And then for this last segment here, going from ice at 0 degrees to ice at negative 10 degrees, we have the heat capacity for solid water times the natural log of T2 over T1. Make sure you pay attention to which heat capacity you're using. The heat capacity of a substance can change with temperature and which state, if it's solid, liquid, gas, etc. phase. Now, since d over the derivative of v squared with respect to v is equal to 2v dv, then the cyclic integral of v dv is equal to the cyclic integral of the differential of v squared over 2. And that's going to be equal to the cyclic integral of d of v times v over 2. And that's going to be equal to 0. Now, let's talk about mixing different inert gases at constant temperature and pressure. Well, there's no chemical reactions because we said they're inert gases. So we're going to start out with them separate. We have gas A over here on the left, gas B over here on the right. I drew them circles and squares just so you can tell them apart. This is the before picture. So this is going to start out at pressure and temperature. They're both the same. And then the volume of A molecules, the volume of B molecules. Remember, this is the entire volume here. And then likewise, you have the pressure and temperature, the volume of these B molecules, and then the number of B molecules. So the after picture, you remove that barrier, you let them mix, then you have A and B all mixed in together. See handout figure 12. So we want to find the entropy of mixing for this irreversible mixing. Now we're going to assume perfect gas, constant temperature. Well, we assumed constant temperature and pressure. So delta U is equal to 0 because U is a function of temperature only for a perfect gas. So step 1, we're going to do the expansion of each gas separately to the final volume. Now, we are actually going to allow energy in or out to compensate for work, if we do any work. So for the change in entropy of 1, it's going to be the change in entropy for the A molecules plus the change in entropy for the B molecules. So it's this expansion that's causing the entropy change. And the answer is delta S1, this is step 1, change in entropy for step 1. For the A molecules, it's just the number of moles of substance A times R times the natural log of the total volume of the container divided by the original volume of the A molecules, plus the number of moles of the B molecules, B substance, times R times the natural log of the total volume divided by the volume of the B molecules. Now remember, that's just for the reversible expansion of final volume. Now, we're going to do the reversible isothermal mixing of the expanded gases. Now we know that delta U is equal to 0 because it's isothermal, and U is a function of temperature only for an ideal gas or perfect gas. Now the work is roughly 0 because since it's reversible and the pressure equalized on both sides of this membrane. Now we know Q is equal to 0 since delta U is equal to 0 and W equals 0. And so we know this is an adiabatic process now. So we get delta S is equal to 2. So the change in entropy for this step 2 is equal to 0 because this step is adiabatic. So then we get the change in entropy for state 2 is also equal to Q2 over T2. So therefore the heat's going to be, the Q is going to be equal to 0. No heat exchange. Now we also have the change in entropy of mixing then. So we have the entropy for step 1, the expansion, and the change in entropy for the step 2, the mixing. So the part 2 was 0, so it's actually the change in entropy of mixing is just from the expansion of the gas. So it's equal to Na times R times natural log of V over Va, and then plus NB. This is a subscript B, remember. Hopefully that's clear there. So the number of moles of B, substance B, times R times the natural log of V over Vb. So we want to replace these terms over here, these fractions, V over Va and V over Vb. Now using PV equals nRT, we know the volume of A is equal to number of moles of A times R times temperature over pressure. We know the volume of B is equal to the number of moles of B times R times temperature times pressure. Now V, the total volume, is equal to the total N times R times T over P. Now we're going to use X to denote mole fraction. So X of A is going to be the mole fraction of A. So X of A is going to be Na over Na plus B. This should probably go all the way over there. So V over Va is equal to Na plus Nb over Na. And that's going to be 1 over Xa. And likewise, V over Vb is going to be Na plus Nb over Nb. And that's 1 over Xb. So, substituting back into that other equation, we have the change in entropy of mixing is going to be equal to minus the number of moles of substance A times R times the natural log of the mole fraction of A, minus the number of moles of substance B times R times the natural log of the mole fraction of B. So the change in entropy of mixing is equal to minus R, factor out the R, times Na ln Xa plus Nb ln Xb. Remember, A is 8.314 joules per mole Kelvin. This is for a perfect gas, constant temperature and pressure. Now the change in entropy of mixing is always positive since the mole fraction of A is less than 1 and the mole fraction of B is less than 1. And if you were to do 20 substances, all those mole fractions would all be less than 1 also. The increase of entropy then is from mixing and not the volume change. Now, if A is equal to B, then delta S mix is equal to 0. For a pure state, XA is equal to 1. Mole fraction of A is equal to 1, so delta S is equal to 0. So the change in entropy of mixing is equal to minus R times the number of moles of A times the natural log of mole fraction of A plus the natural number of moles of B times the natural log of the mole fraction of B. So if they're the same thing, we get change in entropy of mixing is equal to minus 2R times the number of moles of A times the natural log of mole fraction of A. But XA is equal to 1, so the natural log of XA is equal to 0. So change in entropy of mixing is equal to 0.